Hello everybody and welcome to Cranky Calculus. We have started this new series where we're just reviewing for the AP exam. We have units 1 through 4 done. We have unit 5 up next. I've been outsourcing this to my students who've been doing a fantastic job, except now it's a long weekend and they're kind of slacking off a bit. So I'm going to step up here. I'm going to do the MCQ part of this. I hear the FRQ is going to be done by one of my students still. But make sure you like and subscribe to get more content and use these to help you with the AP exam, and best of luck to you, by the way, on the AP exam.
Hello everybody, welcome to another Cranky Calculus video. I'm your cranky classmate, ready to help you with some more AP Calc AB and BC unit review. Today, we're reviewing Unit 5, specifically Extrema, Canada's Test, and Mean Value Theorem. We have an FRQ and MCQ ahead of us, so let's get started. So, question 1 of this FRQ wants us to consider the function f of x, which is equal to x minus 3x to the 1/3. And it wants us, for part A, wants us to find all values of x where f of x has a local maximum. So we know to find local extrema, we first have to take the derivative. So let's do that. We'll label this as f prime of x, which is equal to the derivative of x is 1, and then the derivative of 3x to the 1/3 is just power rules, so that's going to be x to the negative 2/3. Oops. And I'll rewrite this as 1 minus 1 over cube root of x squared, and you'll see why in a second. So now that we have our derivative, we have to find the critical points. Remember, the critical points are where the derivative is equal to 0 or it's undefined. And because we have a term that has an x in the denominator, we can pretty easily tell where x is undefined. It's just undefined where this denominator is equal to 0. And if you plug in a 0, it'll be equal to 0. So we know that x equals 0 is one of our critical points. Now, to solve for the others, we have to set this equal to 0. So let's go ahead and do that. 1 minus 1 over cube root of x squared is equal to 0. And just from looking at it, we can tell that x equals 1 is a solution, because if you plug in a 1, you'll get 1 minus 1 over 1, which is just equal to 0. And because this term on the bottom is squared, we can actually figure out that x equals negative 1 is also another one of our critical points. Because again, you just plug it in, you get 1 minus 1 over 1, which is equal to 0. So now that we know x equals 0, negative 1, and 1 are our critical points, we need to figure out where the sign of the derivative changes. Easiest way to do this is with the sign chart. Let's go ahead and draw a number line here. And we have negative 1 here, we'll have 0 here, and we'll have positive 1 here. So to figure out the different signs of these intervals, the easiest thing to do is just pick a number in that interval and plug it into the derivative and see what the sign of the derivative is. So I'm going to start with this interval over here from negative infinity to negative 1, and I'm going to pick negative 2 because I know it's in that interval. So let's go ahead and plug in. So we'll do 1 minus 1 over cube root of the square root of negative 2 squared is just 4. And because I know that this term right here is going to be is going to be less than 1, I know that if I subtract it from 1, it'll give me a positive output. So what I'm going to do is just label, oops, not meant to do that. I'm just going to label that interval as positive, and I'll label it in green. So next we have negative 1 to 0. And for this I'm going to use negative 1/8 as my x value. So let's go ahead and plug in 1 minus 1 over cube root of the square root of 1/8 squared is 1 over 64. And this is just, and the cube root of 64 is just 1/4, so this is equal to 1 minus 1 over 1/4. And because you have a fraction in the denominator here, you can just move this to the top and take the reciprocal. And this will give us 1 minus 4, which is equal to negative 3. Now there's a negative there, so we know that the integral is, or not the integral, sorry, on the interval, the derivative is negative. So I'm going to go ahead and erase this so we have space. And I'm going to label our interval as a negative. do it in red. So next up, we have from 0 to 1. And for this, I'm going to use positive 1/8. So I'm going to do it again. 1 minus 1 over cube root. 1/8 squared is 1 over 64. And we actually just did this, and because the x squared term makes everything positive, we know the answer is equal to -3, which is again just a negative value. So we can go ahead and label this as negative. And I'll erase all this. And we can actually use a similar method to figure out the last interval from 1 to infinity. We'll use a positive 2 this time. And we'll do 1 minus 1 over cube root of 2 squared is 4. And because I know that this term is going to be less than 1, I know it's going to yield me a positive output. So we have our sign chart done. But now we actually need to figure out, remember, it wanted us to figure out where the local maximum was. So to do that, we have to figure out where the derivative changes signs, but not just changes signs, we have to know that it changes from a positive slope to a negative slope. Because remember, that's what creates an absolute or a local maximum. So if we look on our sign chart, we can see that the derivative changes signs at -1 from positive to negative, and then it doesn't change signs at 0, it stays negative, and at 1 it changes from negative to positive. So remember, we want the one that changes from positive to negative, so that's -1. So we know that -1 is our answer. So we'll say that f of x has a local max at x equals -1 because, let me zoom out here, because f prime of x changes signs from from positive to negative. And yeah, so that's your answer. And remember, the sign chart that we drew here, this is actually not a justification. This is just to help you write out your work and think through the problem. You cannot use it as a justification. You have to say that f prime of x changes signs from positive to negative. And you have to include the positive to negative part too. You cannot just say it changes signs. You have to include that. So that's part A done. Let's move on to part B. Okay, let's move on to part B. So part B wants us to find all values of x where f of x is increasing and concave down. And it wants us to give a reason for our answer. So I went ahead and wrote f of x over here. And remember, it wants us to find where f of x is increasing. And concave down. So we know that in order to find where a function is increasing or decreasing, we need the first derivative, and to find concavity, we need the second derivative. So remember, concave down will happen when the second derivative, or f double prime of x, is less than 0. So I think the easiest thing to do is to go ahead and write down f prime of x. And we actually already did this in the first problem, so we can just go ahead and copy it down. And the cool thing is, to find out where f of x is increasing and decreasing, we can actually just copy down our sign chart from the previous problem. So let's go ahead and do that. Critical points at 0, 1, -1. It went positive, negative, negative, positive. Okay, so remember, we want to find where f of x is increasing, meaning we want to find where f prime of x is positive. Now it's only positive in these two intervals, from -infinity to -1, and from 1 to infinity. So let's just keep that in mind. Now, let's figure out the concavity. So in order to figure out the concavity, remember, we need to take the second derivative. So I'm going to go ahead and write that down right here. So we have f double prime of x is equal to the derivative of 1 is 0. Derivative of -2 over 3 or x to the negative 2 over 3 is just power rule, and this will give you a 2 over 3 x to the power of negative 5 over 3, because we have to subtract 1. And I'm going to go ahead and rewrite this as 2 over 3 cube root of x to the 5th. And I did this for the same reason I rewrote the first derivative. It's just so that we can make our sign chart and find our critical points a little bit easier. So remember, critical point where the derivative is either equal to 0 or undefined. Because we have no x term in the numerator here, we know that it will never equal 0, but we do have an x term in the denominator, so it is going to be undefined somewhere, and that's where x is equal to 0. So we have a critical point for f. We have a critical point at x equals 0. Now, it's a similar process to the previous problem, finding out where the second derivative is positive and negative, and to that we can just plug in. I'm going to go ahead and plug in a negative 1, so that'll get us into this interval right here. So if I plug in a negative 1, 2 over 3 times the cube root of negative 1 to the 5th is negative 1, because we're raising negative 1 to the odd power. And the cube root of negative 1 is negative 1, so that'll give us negative 2 over 3, meaning that this area is negative. So now that we have that, let's go ahead and plug in a positive 1. So that'll give us this interval. So we'll go ahead and do that. 2 over 3 cube root of 1 to the 5th is 1. So that's equal to 2 over 3, which is a positive value. So we know that this is positive. Now, we haven't answered the question yet, so let's go ahead and do that. Oops, I meant to erase that. Let me go ahead and do that. Yeah. So it wants us to find where f of x is increasing and concave down. If we look at our intervals, f of x is increasing from negative infinity to negative 1 and from 1 to infinity. And f of x is concave down where the second derivative is less than 0. We know the second derivative is less than 0 from negative infinity to 0. So we know that the interval where the function is increasing and concave down cannot be from 1 to infinity, because the second derivative is positive. So we know that it is from negative infinity to negative 1. So let's go ahead and write that down. F of x is increasing and concave down on negative infinity to negative 1, because the or actually, instead of saying the first derivative, I'll just put f prime of x. F prime of x is positive, and f double prime of x is negative on that interval. So there we go. Let's move on to part C. Okay, moving on to part C. And before we attempt part C, I just want to make sure that you guys are subscribed, liking the video, hitting the bell icon, and commenting what your favorite part of this video was, or what you thought was the hardest part. So yeah, go ahead and do all that, and let's get into part C. So it wants us to find the absolute minimum value of f of x on the interval 0 is less than or equal to x is less than or equal to 8. Now, whenever a problem says absolute minimum, you want to think candidate's test. So let's go ahead and do that. So candidate's test, remember, starts by always taking the derivative. So let's go ahead and do that. F prime of x, and we've actually done this like twice now, so we can just write it down. So now we have the derivative. We need to find, remember, we need to find the critical points. And we already did that in the previous problem. So we'll say that f prime of x equals 0 at x equals negative 1, 1, and f prime of x is undefined. I'm just going to abbreviate here. at x equals 0. Now, if you actually look at our interval, 0 is already taken care of because it's actually asking us, it's one of the endpoints for our interval. And -1 actually is not in our interval. So we actually do not have to worry about -1. So we can just go ahead and cross it off. We only have to worry about 1 as our critical point. So now that we have our critical points and we have our original function, we can go ahead and set up a table. So I'm going to go ahead and do that. Oops, wrong color. Let's get that back to black. And we'll put x over here and f of x over here. So we have 0, 1, and 8. And all we have to do is just plug in our values, our endpoints and critical points into f of x, and whichever one is the lowest, gives us the lowest f of x value, that is our absolute minimum. So if we plug in a 0, it's just going to be 0 minus 0, so that's 0. If we plug in a 1, we're going to get 1 minus 3 times 1 to the 1/3, which is just 1 minus 3, which is equal to -2. So we have -2. And if we plug in an 8, we get 1 minus 3 times 8 to the 1/3, so cube root of 8, which is 1 minus 3 times 2. Or sorry, not a 1. That should be an 8. 8 minus 3 times cube root of 8. I was just testing you guys, don't worry. I knew it was wrong. 8 minus 3 times the cube root of 2, which is 6. So 8 minus 3 times 2, or the cube root of 8, which is 2, and then 3 times 2 is 6. So 8 minus 6, it gives us 2. So we have 2. And we can see here that the lowest value is -2. So we can go ahead and answer the question. We'll say, and I think this is the best way to answer these types of questions, and I'll give you guys a sentence stem. We'll say f of x has an absolute minimum of -2 at x equals 1 on 0, 8. And you cannot just say that f of x, sometimes the problem will ask you find the x value at which f of x has an absolute minimum. And in that case, if you say the actual value of the absolute minimum, you won't get the point. So this sentence, if you just say something like this, f of x has an absolute minimum of this number at this x value, then you'll get the point because you're knocking out both the absolute minimum and the x value at which it occurs. So that's part C done. Let's go ahead and move on to part D. Okay, moving on to part D. So this one asks us if the mean value theorem can be applied to f of x on the interval from -1 to 1 to guarantee a value c for such that f prime of c is equal to the average rate of change on that interval. So this is just a mean value theorem problem, and if we remember, the conditions of mean value theorem are that f of x has to be continuous, and that f of x is differentiable. So let's go ahead and start checking. So we want to know if f of x is continuous. Well, I have f of x right here. And we know that this x term, there's no discontinuities there because it's just a linear term, so there's no discontinuities. And here, 3x to the 1/3, we know that that's also continuous everywhere. So we can say, yes, f of x is continuous. Now we have to check if f of x is differentiable from -1 to 1. Now, let's go ahead and write down our f prime of x, which we've done like 1,000 times right now. So x to the -2 over 3. And again, I'm going to rewrite this as 1 minus 1 over the cube root of x squared. And we can see here that if we plug in a 0, f of x is actually f prime of x is actually undefined. So this means that there is at a point on f of x that is not differentiable. And remember, 0 is within our interval. So we know that f of x is not actually differentiable on the interval. So we can go ahead and answer the question. Remember, the question is asking us, can the mean value theorem be applied? Not what the value of c is. So it's just a yes or no question. And we can go ahead and answer, and we can say no, because f of x is not differentiable at x equals 0. There we go. That's the FRQ done.
Okay, I'm going to cover the MCQ part of some Unit 5 stuff, which is really going to cover Extrema, Candidates Test, MVT. I am outside at Mikasa, and if you can hear, there might be some dogs barking. I think their owner should probably let them in. If you're a dog owner, like, your dog starts barking, let them in. People outside don't want to hear that stuff at all. Oh, there's a lot of rules on dogs for dog owners that I have. I don't have time for that, but let's go ahead and get to number 2 right here. So we have a function whose second derivative is defined by, and we give you the second derivative. You can see it right there. It's already in factored form. How many points of inflection does the graph of f have? Points of inflection occur when f double prime changes signs. That's super important. It's not when f double prime is equal to 0. We only care about when this changes signs. So what I'm going to do for you here is I'm going to go ahead and make this a sign chart because I already have the zeros of f double prime. So those zeros, as you can see, are going to have a 0, I have a 1, and looks like a -4. So I'm going to go ahead and put those on in order, of course. Okay, so if I'm looking at all my x values, I'm going to look and do this part to the right of 1 first. So I'm looking towards positive infinity. The end behavior is positive. I'm not going to worry about plugging in values. You totally can plug in a value. If you want to, plug in a number that's bigger than 1, like 2, and you'll see that you get positive values. Now it happens at x, or at 1, is x minus 1 is a factor of a power of 1, so it's going to go through the x-axis. So we're going to change signs, and I have talked about that in my previous videos. At 0, it's also a linear factor, and it's going to change signs as well. It means it goes through the x-axis. And at -4, because it's a squared, this works for fourths or sixths, any even powered, it's not going to go through the x-axis. Rather, it's going to be tangent to the x-axis. So I'm actually going to be another positive 1 right there. So when does f prime change signs? Changes signs here at 1 and at 0. So I have an inflection point at x equals 1 and x equals 0. So I have a total of 2 inflection points on that one. That's a tricky one. It's pretty common, so make sure that you know what's going on there. For the next one, number 3, which of the following functions does not meet the conditions applied for MVT? Well, what that means is that f is continuous on the interval, and f prime, actually f prime is continuous too. I won't talk about f prime though. Let's just do f, stick with f. F is differentiable inside the interval. We don't care about what's happening on the interval for the differentiable, so I think that's maybe we're going to get tripped up here. So it's really helpful to know what these derivatives look like. So I'm going to go through that step by step. This is one that probably takes a little bit longer of a question than you really would hope. So for the first one right here, I'll do this in purple. This y prime, oh boy. Technical errors, there we go. So this y prime right here equals 1 over x. So it's got to make sure that the, I'll put a prime right there, that this domain between 1 and e for ln of x, we can plug in values, which we totally can. It's continuous between 1 and e. And then to see if it's differentiable, make sure that the derivative is continuous, and it totally is from here. The only value that we can't plug in on the derivative is 0, so we're good to go. So this is definitely not a, because I'm trying to see where this does not meet. Does not meet. For the next one, it's usually these third power or 1/3 power things where weird stuff happens. So we are continuous here for x to the 2/3. If you want to know, it kind of looks like this. It looks like a little bird. If you want to know what that graph looks like, it's pretty common. So I'm going to worry about the derivative for this. So if I do the derivative for this one, you're going to get 2/3 x to the -1/3, which means that I can't plug in a 0. That's the only thing, because if you look at this, this is equal to 2 over 3 x to the 1/3. I cannot plug in a 0, but since the 0 is an endpoint, because again, we need to be differentiable inside, I don't care. whatsoever. This thing is differentiable between 0. Oh, there's that dog again. Take him inside. I am differentiable, by I mean the graph, is differentiable between 0 and 8. It's not differentiable on 0, but I only care about the n. So, because of that, not B. For C here, this is a rational function, and it looks like we're good to go, because on the only thing I have to worry about for rational function is a vertical asymptote for the original or the derivative. So this one right here, since we have x squared plus 1, that will never equal 0. And if we were to take the derivative of this, I don't really want to waste my time taking the derivative of this, because I know it's going to be quotient rule, and the denominator would just be x squared plus 1 all squared. So I'm pretty sure it's not C. I'm going to check on D, and if it's not D, I'm going to come back up to C to rework that one out. Looking at D right here, I do see an issue, because I do have a vertical asymptote at x equals 1. So since I have a vertical asymptote at x equals 1, this is not continuous. So therefore, this answer must be D. Okay? Probably could have gone through this a lot quicker, but I want to explain everything step by step so you knew which one to choose. If I'm looking at this problem cold, I'm going through real quick just to check continuous, 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 and I probably got this one done a little bit quicker. Let's go ahead on to 4 here. It's known that the tangent line of curve C is, so this kind of looks implicity, slightly differential equation-y. But which of the following must be true at the point -1, 1, and these are all talking about extrema for the most part. So except for 3, which just talks about the slope at C. So what we're going to do here is, because I don't know the original equation, I'm forced to use the second derivative test on this one. So since this is the second derivative test, I need to check that dy dx at the point xy equals -1, 1. Make sure that is 0. I'm going to put a question mark there. So is that true? If I were to substitute in a -1 for x and a 1 for y, that does equal 0. Okay? So because of that, I can knock out 3 right off the bat, because it says the slope of the tangent line of C at -1, 1 is 2. That just means the derivative is 2. That is certainly not true. So it's definitely not 3. So we can cross out C and D. Those are not an option. So now let's go ahead and find that second derivative. This is where the big boys come into play. This is where mistakes are usually made. So the derivative of x is going to be 1 plus the derivative of y is also 1, but since we're taking the derivative with respect to x, we have to tag it with a dy dx. So that's a little bit of chain right there. And so if I evaluate this at, that's the notation for evaluation, by the way. If I evaluate this at -1, 1, we know that dy dx at -1, 1 is 0. So it's going to be 1 plus 0. So this is 1, which is positive. So that means that this thing is concave up. Here's concave up. And somewhere on this curve, we know that at -1, 1, the derivative is equal to 0. So it's going to look like that right there. So that looks like a relative minimum to me. So I'm going to go with B. That's about it. Hey, let's talk about some candidates test here. What is the absolute maximum value? Make sure you're answering with the value of this function right here in the closed interval. For the candidates test, you have to find critical points. You have to test endpoints, test critical points. Largest value is the maximum. Let's do it right here. So I do need those critical points. So I need y prime. Derivative of sine of x is, very good, cosine of x. Derivative of cosine of x is negative sine. And we need to set that equal to 0. When we do set that equal to 0, this can get a little confusing because you're like, which one is this? Does this work? Well, since we can't factor anything out, let's go ahead and set these equal to each other. So when does cosine equals sine? I mean, I know that. It's just going to happen at the pi over 4 family, okay? Or pi over 4, and then in quadrant 1, and then in quadrant 2, they're opposite signs, so it's not going to work. And then also in quadrant 3, but quadrant 3 is between pi and 3 pi over 2. If I'm looking at my interval here, I just go from 0 to pi. So this happens at x equals pi over 4. You really need to know that unit circle. If you're like, wait, I still didn't know that, I didn't get that, here's another way for you. If you divide both sides by cosine, you're going to get 1 equals sine over cosine, which is also tangent. So when does tangent equal 1? At pi over 4, not at 3 pi over 4, that's -1. At 5 pi over 4, but 5 pi over 4 is outside the bounds. So now I'm going to go ahead and make my table here. So I have my x value, I have my y value. So I'm going to go ahead and use 0 because that's an endpoint. I see pi over 4. It's a critical point, and then pi. So we're going to go ahead and substitute these values in. If we have a 0 in for y, we're going to get 0 plus 1, so we're going to get 1. At pi over 4, we're going to get root 2 over 2 plus root 2 over 2. And at pi, you get, what, 0 minus 1, so negative 1. So clearly, it's going to be root 2 over 2 plus root 2 over 2. It's not a choice as written, but this is, if I add these together, I do get just 1 root 2. Answer is B yet again. Let's move on here. We are cooking, at least I'm cooking. Let f be the function where we have that function f. What's the value of the steepest slope of f on the closed interval from 0 to 2? This is another Canvas test question, but steepest slope is going to be the largest f prime value. Steepest slope, I'm going to go absolute value. Largest f prime value, really the magnitude of f prime. Looking for that largest possible value because it doesn't say anything about negative slope or anything like that. That's not the most positive slope or the most negative slope. It's the steepest slope, so we have to consider positive and negatives. That's why I'm going to look at the magnitude of that. So let's go ahead and find f prime. This is a polynomial, so this is not tough. I say that and I'll make an error. Negative 6x squared plus 12x minus 2. Is that correct? I wish I had an audience. I don't have one. I'm just going to hope that I can do this basic math, but you never know. Mistakes do happen. Now, I wanted to the candidates test of f prime. So I need to see when the derivative of f prime is equal to 0. So if you look back here, what we did for number 5 here, to find the maximum value of this y function, we took its derivative and did the candidates test from there. I need to take the derivative of f prime to do the candidates test there. So f double prime of x, another simple one that I am a candidate for messing up. I can do the most complicated things, but I can't do anything simple. So there's the derivative, set that equal to 0, and we're going to get x to equal 1 here. I'm going to spare you the algebra. So we're going to x equals 1. So now when I do my candidates test, and again, I'm looking at the steepest slope, so I'm considering f prime. This is like my OG function right there, where I just starred. F prime is what I care about because I'm trying to find the steepest slope. So I have my endpoints of 0 and 2. I have my 1 right in the middle there. I'm going to substitute these values in. I'm going to have substitute of 0 into the f prime. I'm going to end up with negative 2. Okay. Now I only care. That actually gives me a value of 2 because I care about the steepest part of it. If I substitute it in a 1, oh god. I promise I'm good at math. 4. So that one's going to be steeper than 2. And then if I substitute it in a 2, oh boy. I'm going to have to write this one out. I'm usually better at mental math, but I'm on video. I don't get really good at math. Negative 6 times 4, it's negative 24 plus 24 minus 2. Oh, is that another negative 2? I really hope this is right. I don't feel like remaking this video. So negative 2. I'm just doing it again in my head real quick, make sure I'm good to go. Yep, I believe that's right. So for these values, if I look at the absolute value of these, so if I'm going to make another chart right here, I only care about the absolute value of these. So this is 2, 4, 2. My steepest slope value was, I wrote 4, it should be a 2, is right here. So my steepest slope is 4. I got a calculator question here. I'm going to use Desmos, if you don't mind. Like, you have a choice. For this one, you get Desmos on the exam, but I think it's like totally amazing. Hopefully somebody has taught you how to use Desmos. So let f be the function whose derivative is given. So we have this derivative on the open interval from 0 to 2. Which of the following values does f obtain a relative maximum? Okay, so what I'm going to do here is I'm going to pull up Desmos here in just a second, and then I'm going to sketch this out. Not sketch this out. I'm going to type this out as an f of x. I can't type in the derivative. Actually, maybe I can. I don't really know. I'm going to go ahead and pop over to Desmos right here. So you can see that I typed in the function over here. You know, if I was better at Desmos, you could probably see everything. But I said this is f of x equals, so I typed this thing in. This is what it gave us. Okay. So we have a value here. I'm going to just, if you click this little button right here, it'll export it over here. I'm sorry, you can't see everything. I'm not technically savvy person. And then same thing, if I click this here, I can export that over here. So I can kind of bounce between these two things right here. This is f prime. So what we want is we want a relative, I already forgot, maximum. Relative maximum. That is when f prime changes from blank to blank. What's the blanks? It's from positive to negative. So f prime is positive here, negative here. It's going to be at red dot. We're changing from positive to negative. So if I were to do a sign chart of this thing, the values that I got was 0.651, and I got 1. So this is what f prime is doing. So that means that f down here is doing this. So I do a relative maximum here at 0.651. And that's going to wrap up our MCQ section here. Thanks so much for watching. Thanks so much for sticking around and giving us those views, those view hours. Really appreciate it. Best of luck to you in the AP exam, and don't forget to like and subscribe.